All right, let's get started. I don't know where everybody else is, but I'm here. You're here. Let's get going. All right, I'll be sending out an email later today to remind everybody, check your lab stores 1 through 12, except for the one today, due today. I should have graded it. If you handed it in, there should be a grade in Blackboard for you. If there's not, email me, I'll check, but the other thing is send me an email. And I see we have another a special guest today. Hi, special guest. Anyways, let's get going. So today I'll send out that email by Wednesday. Let's make it 1 p.m. You should have all labs submitted because I've got to get the grades out in time next Monday or earlier to COD. So please get the labs in if you haven't already. All right. Another thing which I normally do the last week, and right now this is the last week, is I tell my students, so you're my students, I better tell you, if you like what I've been doing this summer, go to ratemyprofessor.com and let people know. If you didn't like what I was doing this summer, go to ratemyprofessor.com and let people know, get away from Dr. White, but let them know. Now, listen carefully. If you really, really like what I've done, send an email to Dr. Cavuto, the president of COD, copy to Board of Trustees. You'll see in Blackboard, I have a folder or an area for special emails. His email and the Board of Trustees are there. And if you do that, I'd highly recommend write it, let it sit for a day, look at it again, and then send it. That way you'll make sure you've done a good job. And if you do send it to them, don't say, hey, Dr. Caputo, do something more professional like dear Dr. Caputo or hi, doctor. But if you really, really, really like what I've done, send him an email, copy the Board of Trustees, and let them know. And if you really, really, really didn't like what I did, do the same thing. Send them an email and copy the Board of Trustees. I should point out years ago, unbeknownst to me at the time, the whole class sent emails to the Board of Trustees, and that's when I won Outstanding Faculty of the Year Award. But now it's time to get to work. All right, remember, Thursday, I'll be sending out the final exam, excuse me. And if you look, you'll be able to see on Blackboard the point cut down. One thing I didn't mention, to make your life just a little easier, the first part of the final will be on test number 1 material. Second part of the final will be, guess what, test number 2. The third part of the final next will be, I'm out of focus, now I'm not, test number 3. And finally, the last part, well, second to last part will be from test number 4 material. And then we'll have the very end somewhere, I'll have new material, stuff on nuclear stuff. All right, I want to get going on material from test 2. I started a review yesterday. Let's continue. Thumbs up, people. Can you see test review? Thank you. All right. Now, we talked about electron configuration and then valence electrons. You should know valence electrons. You should know the definition because I asked on test number 2, what are valence electrons? They're the outermost electrons of an element. You go and look at the top of the column of the periodic table. And let me pull one up while I'm talking to you. And that will give you the number, whether it's Roman or numeric, which I put on my table. That will give you how many valence electrons are in that All right, why can't I find it? It's Murphy's Law time. Bingo, got it. All right, you all should see the periodic table on your screen. And the numbers on top in red. Thumbs up, people, to see the periodic table? Nope. Uh-oh. Zoom tells me you should, but let's do this. Now do you see it? Thank you. Zoom plays games when you're sharing. All right, let's get back to work. Periodic table on top. If you look at the column, the numbers I have in red, those tell you how many valence electrons. Nitrogen 5, carbon 4, sulfur and oxygen 6, halogen 7, the noble gases 8. And you should know how to find the periodic table and where the valence electrons are. All right, you should know how to draw a Lewis structure. When you do that, it's only talking about the valence electrons. You take the element's chemical symbol. On each side, you put one dot for each valence electron, and you do that on each side, one on each before doubling up. A number of you have made a mistake on test 2 by not doing that, and I mark it wrong. Next, I start talking about chemical bonds. There's 2 types of chemical bonds, ionic and covalent. You should know, as I asked in test 2, what is an ionic bond? Ionic bond results from the transfer of one or more electrons from one atom or group of atoms to another atom or group of atoms. A covalent bond results from the sharing of one or more pairs of electrons between atoms. Here you're sharing one or more electrons or transfer, not sharing. Here in covalent, you're sharing pairs of electrons. The Octet Rule, which I'll never ask you, but it's important to understand that for forming chemical bonds, i.e. that is compound formation, atoms of elements lose, gain, or share electrons in such a way that their electron configuration is identical to that of the nearest noble gas in the periodic table, which is 8 valence electrons. And I showed you in terms of how do you form an ion? Well, an element can lose or gain electrons to get the same number of valence electrons as the nearest noble gas based on atomic number. And if we look at calcium, remember, atomic number tells you how many electrons and protons. Calcium has 20 electrons, 20 protons. What's the nearest noble gas to calcium? Everybody see the periodic table? Thank you, thumbs up. I don't even have to say thumbs up, people, anymore. If you notice, calcium here at 20, the nearest noble gas numerically is argon at 18. Therefore, calcium wants to lose electrons, and it goes to 18 electrons, but it still has the same number of protons. And therefore, it has 18 times -1. Each electron is a -1. Each proton is a +1. You add it together, it's a +2. The question would be, show the ion, and you show it by the chemical symbol superscript the charge. And you can write, if the charge is just 1, you put a plus or minus. If it's more than 1, you can have +2 or 2+, or you have minus for another thing like oxygen, -2 or 2 minus. All right. Formula of ionic compounds indicates the number and kinds of ions that make up the ionic compound. And remember, the sum of ionic charges in a formula of an ionic compound is always 0. Actually, all molecules in nature have a net 0 charge. And what that means is, everybody see test 2 key? Thank you. We look at problem 11. Write the chemical formula for the simplest compound of the following pairs. And here we have lithium as a +1, bromine as a -1, add them together is 0. Therefore, that's what the 3 little dots mean in math. And Dr. White thinks it's cool, so that's why I used it. Lithium bromide has 1 lithium, 1 bromine. Now, this one, you have beryllium nitrate, and beryllium, Be, you don't have to know it's beryllium, but you know it's a +2. This is a -1 polyatomic ion, and therefore, if it's -1 and +2, that doesn't equal 0. You can't change the charge, but you can change how many there are, and therefore, how do you do that? You put a 2 there. So +2, -2, 0. How do you show that? 1 beryllium. 2 nitrates, when it's a polyatomic ion, you put it in brackets, subscript to the right, 2. And let's get back to the review. Now, when we talk about covalent molecules that's sharing pairs of electrons, and you show that one way is by Lewis structures. And you have in a Lewis structure bonded electrons, pairs of electrons that are shared between atoms in a covalent bond. Non-bonding electrons, pairs of valence electrons that are not involved in sharing. And remember, this is something extremely important. Covalent bond, there are 3 of them. Single bond, 1 pair of electrons. Double bond, 2 pair of electrons. Triple bond, 3 pair of electrons. I'll say it again. Single bond, 1 pair of electrons. Double bond, 2 pair of electrons. Triple bond, 3 pair. I asked a question like this on test number 2. I thought I did. Yeah, right here. And a lot of you got this totally wrong. Remember, when you're taking a test, take the time to read the question carefully. And it says name 2 types of covalent bonds and indicate how many pairs of electrons are involved in each type of bond. And you only have to name 2 of the 3, single bond, 1 pair, double bond, 2 pair, triple bond, 3 pair. This is something you should know. Now, all molecules want to have an octet. With covalent, you have to have an octet. And if you look at problem 6, what would be the simplest molecular form, molecular compound form between the pairs of elements? In other words, write the molecular formula. Nitrogen has 5 valence electrons, iodine 7. But if you look here, nitrogen has 3 unpaired, iodine 1. Nitrogen has 5 total, it wants to get to 8. Iodine can only share 1, so you need 3 of these for 1 of these, nitrogen triiodide. We look at carbon and hydrogen. Carbon has 4 valence electrons, hydrogen has 1. Carbon wants to get to 8. The only way you can get valence electrons is from hydrogen. It needs 4 more, therefore 1 carbon, 4 hydrogens. And that's how you do it. I don't have it listed here, but you should know how to draw the Lewis structure for various compounds or molecules. And how do you do that? You deal with the valence electrons. For water, one hydrogen has one valence, oxygen 6, put the oxygen in the center. It has 6, it gets one more from each hydrogen. It has this octet. Remember, hydrogen's octet is only 2. Now, B is one you most got wrong. Let's look at it. Whenever you see an alkali metal, sodium, potassium, or lithium, it will always form a cation. I know of no example where they are ever in a covalent bond. In fact, I've asked other chemists where I teach at both schools, and there are none. Nobody knows of any because there are none. Therefore, potassium forms a cation, +1. Carbon and potassium cyanide has 5 valence electrons. Carbon 4, nitrogen 5. And let's go through, even though it's on the paper. So over here, potassium will give up its electron. Carbon has 4 valence electrons, nitrogen has 5, and if I go over here, you don't have to do this. If you look here, nitrogen has 3 unpaired electrons, carbon has 4. And the carbon says to the nitrogen, hey, I have 3 unpaired electrons. You have 3 unpaired electrons, and you can't see this. Somebody should have, says screen, but let me ask now. Can you see it now? Yep, okay. Said screen, but all right, let's go back. Potassium cyanide. Potassium always forms a cation. Nitrogen has 5 again. Oh no. All right. Now can you see it? All right. I'm just not going to move so it will not go away. No, I got to move. All right. Let's try it again. 3rd time's the charm. Potassium always forms a cation. Carbon has 4 valence electrons. Nitrogen has 3. So carbon says, I've got 3 valence electrons. You've got 3 valence electrons. Let's share. Nitrogen still has its non-bonding electron pair right up here. It's still there. Now, where did the electron that potassium had go? It went over here. And now, instead of having 9 total, 5 plus 4, it has 10. So that means it has an extra electron. It has a negative charge. And that's why this is the correct way. And that's something to remember. Most students get this wrong, which they did on test 2. Whenever you see a alkali metal, alkaline earth metal too, but I've never put that on test. Oops, I gave away something. But any alkali metal, sodium, lithium, potassium, always form a +1 ion, cation, and give up its electron somewhere. And that's why this is in a negative in a bracket, because it's the cyanide atom. All right, everybody see mole and mole calculation? Thank you. All right, let's talk about one of my favorite and most important subjects in chemistry, the mole. Remember, a mole isn't a furry little animal that digs hole in the ground. A mole is the chemist's counting unit. Now, important relationships you should know. And let me shut off spell check so the little lines go away. One mole of an element equals Avogadro's number. Avogadro's number is 6.02 times 10 to the 23rd. This should be superscript. Let's see if I can do that now. I can. And therefore, you should know Avogadro's number is 6.02 times 10 to the 23rd. One mole of an element equals Avogadro's number, atoms of that element. One mole of a compound equals Avogadro's number of molecules of that compound. So we have a relationship between moles of an element or compound and either atoms or molecules, Avogadro's number. Now, let's take a look at how to use that relationship. And since Zoom is being zoomy with me, everybody see the test key? You see where it says, what is Avogadro's? Thank you. All right, now, here, if we look at number 15, 6 points, how many moles are in 1.204 times 10 to the 43rd molecules of sodium nitrate? We're trying to find moles of sodium nitrate. We're given how many molecules. And now it's time, oh, I haven't done it all day today. It's time to use your good buddy, your good friend, unit analysis, and it has been my good buddy. And I think most of you have gotten the hang of it too. What do you have to start with? This number. What are you trying to get to? This number. Whatever units you're trying to get to goes on top of a ratio. Whatever units you're trying to get rid of go underneath a ratio. Where do you get those numbers? That one mole equals Avogadro's number of molecules, which you'll be given on test on the final. And let's remember, when you do multiplication division, you get the same number of significant figures in the final answer as the number you get start with, or multiply and divide, that has the fewest significant figures. This is 4. This is 1. Oh, wait, this is an exact number. This is 3 significant, so our answer is 3 significant figures. And that's how you do it. All right, everybody see a blank page? Thank you. My W's are looking awful today. And why don't you try doing this one yourself? You don't have your calculator, just set it up. Go. All right, I think everybody's done. Let's go ahead and do this. And the question is, first, what are you trying to find? What are you given? You're trying to find molecules of water. What are you given? 5.713 moles of water. Well, it's time to use your good buddy unit analysis. This is all we have to work with. This is what we're trying to get to in terms of units of our answer. And therefore, we'll use unit analysis. Whatever we're trying to get to, we put on the, or get rid of, we put on the bottom. Whatever units we're trying to get rid of, we put on the top. And where do you get that? Important information, 1 mole compound, which water is, equals Avogadro's number, molecules, compound. I could have put here water, and same thing here, water. Therefore, for every 1 mole, there's 6.02 times 10 to the 23rd. Before I pick up my calculator, I'll say moles of water divided by moles of water. Anything divided by itself becomes number 1 is gone. I'm left with the right units, molecules, and now I'll go to my calculator. And this is the number I get. And if you go back and look at the numbers, first one is 4 significant. Avogadro's number is 3 significant. We round this off to 3, keep the 3, keep the 4, keep the 3, use the 9 to round off, that's 5 or higher. Drop this, increase that to 4 times 10 to the 24th. Go back to my screen. Let me check because I've been having, everybody see the problem now? Thank you. And we put in here the correct answer is 3.44 times 10 to the 24th. And that's how you use your good buddy unit analysis in that type of problem, which obviously I had on test number 2. Let's go back and look at test number 2. Actually, first let's go back to the review. Anybody getting dizzy? Hold on. And other things that you will be given are 1 mole of a compound, 1 mole of an element equals its atomic weight of that element in grams, and 1 mole of a compound equals the molecular weight of that compound in grams. And the molecular weight of a compound is the sum of all atomic weights. And as I just showed you, remember on the final to use your good buddy, hold on, I got to do it, your good friend, unit analysis. And let's take a look at one. Eight points. How many moles are in a sample of 0.0822 grams of oxygen? Well, the one thing I forgot to mention that was on the review was the molecular weight of a compound is the sum of all atomic weights. And on the final, like the test 2 and 3 and 4, use 3 significant figures for all atomic weights. So how do we proceed? Well, first of all, I get my red pen going. And we're being asked how many moles are in a sample of water or oxygen. And I give you the formula for oxygen. So what are we being asked to find? Moles of oxygen. What are we given? Grams of oxygen. This is the only number I have to start with, so I put it there. Here's the units I want to get my answer in. If there's a ratio that I can multiply this number to get to this units, how do I find that out? Use your good buddy, your good friend, unit analysis. Remember, I'm still going for the Guinness Book of World Records for saying the most times your good buddy, your good friend in a semester. Whatever you're trying to get to, you put on top of the ratio. Whatever units you're trying to get rid of, you put underneath. Where do you get these? From 1 mole compound equals molecular weight in grams of the compound. And the molecular weight is the sum of all atomic weights. So if we look here, molecular weight of oxygen in grams, there are 2 oxygen atoms. The atomic weight of oxygen to the 3 significant figures, 16.0. This is an exact number 2. And therefore, the molecular weight of oxygen is 32.0 grams, which I put here per 1 mole. Now, here we have oxygen, 3 significant figures to weight. This is 3. The molecular weight. 1 is an exact number because that's part of the definition. Therefore, our answer should have 3 significant figures, and it does. And it's time for Dr. White to let you have some fun. Since you may not have it handy, those are the atomic weights of hydrogen and oxygen, the three significant figures. Why don't you just try and set it up? Go. When you're done, smile or give me a thumbs up. I see 2 thumbs up. If you're not on video, if you can click on the thing to give I see 3, 4. I'll give you about another 30 seconds. Those of you who are faster than others, please be patient. I try and give everybody time to finish. All right, let's do it. What are we being asked to find? Grams of water. What are we given? How many moles of water? And important information, 1 mole of a compound equals the molecular weight in grams of the compound. And the molecular weight is the sum of all atomic weights. So what do we have to start with? This, moles of water. What are we trying to get to units of? Right here, grams of water. And now it's time to use your good buddy, your good friend, unit analysis, without sound effects. And whatever you're trying to get to goes on top of the ratio. Whatever you're trying to get rid of goes underneath. And therefore, moles water, grams of water, 1 mole equals the molecular weight of water. Ooh, we got to do that. Water, 2 hydrogens. One oxygen. Each hydrogen has atomic weight of 101. The 3 significant figures, the oxygen has atomic weight, if you look on the periodic table, of 16.0. Remember, when you're adding, you get the same number of significant figures past the decimal as the number that has the fewest significant figures past or to the right of the decimal. This is 1, this is 2. Therefore, this is the lowest number. Therefore, I keep the first significant figure past the decimal, use this to round off. It's 4 or less, I drop that. This is 18.0. And now I can go to my calculator. Oh. And here's the number I get. If you look at the numbers, the first number was 4 significant figures. The next one was only 3. Round this off to 3. Keep the 6, keep the 9, keep the 4. Use this number. Ooh, it's 9. That's, once again, 5 or higher. Drop that. This becomes 6.95 times 10 squared. And that's your answer. And that's how you use those relationships. Next, I talked about a chemical equation. Chemical equation shows what happens when you have a chemical reaction. At the base of the arrow are your reactants, which I also call starting materials. At the head of the arrow are products. Now, balancing chemical equation, you should have the same number and same type of elements on each side of the chemical equation. You can't change the formulas, but you can change the number in front, the coefficients. Remember, leave hydrogen, oxygen last. That's my suggestion. It's always worked for me. Remember the even odd trick. If you have even number of atoms on one side and odd on the other, you multiply the two side numbers together and then divide the coefficient into that multiplication. And that's how many atoms you should have on each side. And we went through that on test 4. On the final, I think I have 3 or 4 balanced chemical equations similar to what I did on test 2, so know how to do them. Go back and do the practice problems. You also had a lab with a lot of practice problems, and you should be good. Most people did good on that. Now, next thing, everybody see mass calculations? Go ahead. All right, mass calculations is when you're asked how many grams of this compound related to in a chemical reaction will make, or you need to make, so many grams of another compound. And this is one of those where you need 3 steps. The first step, whatever you're given in weight, you convert to moles. The second step, now whatever you have in moles, you convert the moles of that to moles of the answer you're trying to get to, that compound. And finally, you convert from moles to grams. And remember, the coefficients of a balanced chemical equation are mole ratios. By the way, here's where we balance chemical equations from test number 2. If you notice here, I have 1 iron, 2, so immediately I put a 2 in front of there. Here I have 1 sulfur. Remember, whatever in the bracket, you multiply times the outside. I have 3 sulfur. I put a 3 there, and then I did my hydrogens and carbon and my oxygens. We did things of molecular weight. I've already shown you how to do that. All right. Hint, know how to do this type of problem. And one other thing I'll mention again, if I put, which I did, balanced chemical equations on the final, the answer is already balanced will never, ever be correct. If I asked you to balance a chemical equation, you have to balance the chemical equation. All right, let's look at this problem. Excuse me. How many grams of hydrogen, H2, tea break time, are needed to react with an excess of nitrogen gas to make 39.1 grams of ammonia? You're given a balanced chemical equation. That's why I say hint. It's really not a hint. It's necessary. You need to do 3 steps. What are you being asked to find? You're being asked to find the weight of hydrogen needed to do what? To make this amount of ammonia. First step, whatever you're given in grams, you convert to moles. How do we do that? 39.1 grams of ammonia. We want to go to moles of ammonia. Use unit analysis. Whatever we're trying to get to goes on top. Whatever we're trying to get rid of goes underneath. And where do we get this ratio of moles to grams? 1 mole of a compound equals its molecular weight. The molecular weight of ammonia, NH3, 1 nitrogen, 3 hydrogens. Multiply, add it up, proper significant figures to using atomic weights to 3 significant figures. The molecular weight of ammonia is 17.0. You put it in. Do the math, but first, grams of ammonia divided by grams of ammonia cancel out. We're left with moles of ammonia, so we knew we set it up right. And now 3, exact number. Here's the number you get, the 3 significant figures. Now, this is one of those problems where you can round off at each step, which is what Dr. White likes to do, or wait till the end. I will calculate it both ways. Both answers are correct. Now, are we done? No, we're trying to get grams of hydrogen. Whatever we converted to moles, we now want to convert to the other thing we're trying to get to in moles. Moles of A to moles of B. How do we do that? We start with moles of ammonia. We're trying to get to moles of hydrogen. Whatever we're trying to get to, we put on top. Whatever we're trying to get rid of, we put underneath. Where do we get a relationship between 2 moles or moles of ammonia, moles of hydrogen? We come up to the balanced chemical equation and see the coefficient 3. That tells me 3 moles of hydrogen react when there's no coefficient. It's 1 mole of nitrogen to make 2 moles of ammonia. Therefore, I get the 3 from this coefficient. I get the 2 for ammonia from this one. These are both exact numbers. 3 significant figures. I put the numbers in. Notice moles, ammonia divided by moles cancel out. I'm left with the moles of hydrogen I want. And now we take this and do the math, and this is the number you get the 3 significant figures. Are we done? No. We're trying to get the grams of hydrogen, and we have moles of hydrogen. And now we'll do step number 3. which is going from moles of B, which in this case is hydrogen, to grams of B. How do we do that? Use your good buddy, your good friend, unit analysis. And here, if you look, we have moles of hydrogen. We want to get the, grams of hydrogen. Fix that quickly. Whatever you're trying to get to goes on top. Whatever you're trying to get rid of goes underneath. And where do we get this relationship of moles of hydrogen to weight? The molecular weight. And for hydrogen, you have 2 hydrogen, I don't have it here, equal 2 times 1.01 equals 2.02 grams of hydrogen. I want to do water, I don't need it here. And therefore, for every 1 mole of water, I got water on the brain. For every 1 mole of hydrogen, you have 2.2 grams of hydrogen. Moles of hydrogen divided by moles cancel out. I'm left with the right units, and therefore I now do the math. 3 significant, 3, 3, and that's how you do it. Hint, you should know how to do this. Can you keep a secret? There will be no limiting reactants on the final. There will be no limiting, oh, I like that. No limiting reactants. Sort of like in baseball. You're out. Well, it's out of the final too. So you don't have to know that. Well, you do it for the rest of your life. It might come in handy. But for my final, there will be no limiting reactants. Let's go back and do a balanced chemical equation. Let's have some fun. And why don't you try this one? Balance the following chemical equation. Go. And when you're done, look up and smile or give me a thumbs up. See a number of you are starting to give a thumbs up. I'll give you another 30 seconds. For those who have finished early, try doing one hand forward, the other backward, and do it at the same time. Don't do that while you're driving. And then when you're done, do that with your thumbs. All right. Dr. White's getting silly, which is fun. All right, let's do this. Leave hydrogen, oxygen last. So I'm going to start with carbon. I have 7 carbons here. Oh, I only have 1. I can't change the formula, but I can change how many to get 7 carbons. I'll do this. Well, now I've got 7 carbons, 7 carbons. Next, well, I have hydrogen and oxygen. I'll do hydrogen. Here I have 16 hydrogen. Ooh, here I only have 2 hydrogen. I want 16. How do I do that? Well, 2 goes into 16 8 times. And now I have 16 hydrogen. And now here I have 2 oxygen, but how many on this side? 7 times 2 is 14 oxygen, plus 8 times 1 is 8 oxygen. And if I do my math correctly, and if I don't, somebody correct me, this would be 11 oxygen, 22 oxygen. I'm getting ahead of myself. How do I get 22 oxygen this way? Take 2, divide it into 22, and we have 11. And now if I look at this, I'll check 7 carbon, 7 carbon, 16 hydrogen, 16 hydrogen, 22 oxygen, 22 oxygen, and it's now balanced. And that's how you do it. And if I look at the clock, we're just about out of time today. All right, special announcement. Because we're having a final, I'll be sending it out on Thursday. Tonight, special only, I will also have an office hour from 6 to 7. If you have any questions, stop by it, and I'll have that. With that, I'm going to let you out a whole 14 seconds early.
Quick question.
I do slow questions.
Yeah, is it the same link for the office hour for today?
I'll have it tonight. Normally, I only have Monday and Wednesday. And if I remember correctly, and I'll check on my computer, it's a Tuesday. For some reason, when I'm not traveling to schools, it's hard to keep track of days. But anyways, I will also have an office hour. If you need any help right now, I'll stay a little later too. Okay?
Perfect. Thank you.
With that, I'm going to say goodbye, everybody. Have a great day. Gay and gesund. Be healthy. And I'll see you tomorrow. Tomorrow we'll go through test 3 material. Bye.